All right, welcome everyone. If you're a student trying to wrap your head around microeconomics, well, you're in the exact right place today. We're going to look at the theory of production, but we aren't just going to sit here and stare at dry textbook math. Instead, we're framing this explainer as your personal, practical playbook for running a successful factory. Imagine you're the boss, right? You have resources, you have goals, and you desperately need a strategy. Well, that is exactly what the theory of production gives you.
Okay, let's dive right into this. There's this huge myth out there that running a business is just about making money as fast as humanly possible. But the reality? It's way more complex. It's honestly like a giant puzzle. You have to balance your inputs, your productivity, and the constraints of time just to figure out exactly how much output you can generate. So, how do you find that perfect sweet spot where you aren't wasting resources, but you're still maximizing what you make? Well, that is the core question literally every producer faces. To solve this puzzle, we're going to break the theory of production down into 5 really manageable steps: the basic production function, short run versus long run, productivity, isoquants, and finally, profit.
All right, step 1, the basic production function.
Before we can optimize anything, we need to figure out what we actually need to start producing goods in the first place. You'll see this formal mathematical definition in your textbooks, but let's translate that jargon immediately. The production function is, quite simply, a recipe. The Q stands for your output, so the cakes you're baking, the cars you're building, the abs you're coding. The F just means it's a function of your inputs. And what are those inputs? Well, primarily they're L for labor, meaning your workers, and K for capital, meaning your machines, your buildings, your equipment. Simply put, output equals what happens when you combine your workers and your machines.
Moving right along to step 2, short run versus long run.
Now that we know what goes into our factory, we absolutely have to talk about time. And how economists define time is completely different from how we define it in our everyday lives. In economics, the short run doesn't mean a few weeks, and the long run doesn't mean a few decades. The short run simply means you are stuck. It's a period where at least one of your inputs, usually your heavy machinery or your factory building, is totally fixed. I mean, you can't just magically snap your fingers and build a new warehouse overnight, right? But the long run, that's a period where everything is variable. You have enough time to change your machinery, expand your building, and completely overhaul your operation. The long run gives you ultimate flexibility.
Actually, to really hammer this home, there's this fantastic quote directly from the source material. The short run is a nebulous concept. It can be a day, a month, a year, or even a nanosecond. This is a wildly counterintuitive textbook fact, but it's absolutely crucial to remember for your exams. Time in economics is not about the clock ticking on the wall. It is purely about how fast you can acquire new equipment. If it takes you a full year to buy and install a new manufacturing robot, then your quote-unquote short run lasts exactly 1 year.
Okay, step 3, productivity, marginal, and average.
All right, so we know our inputs and we understand our time constraints. Now let's evaluate the workers inside our hypothetical factory to see how productive they actually are. You're going to hear the word marginal a lot in economics, and it can sound incredibly intimidating. The textbook calls it the first partial derivative of the production function, but in plain English, marginal product is literally just the extra stuff you produce when you hire exactly one more person. If your factory makes 100 shoes and you hire one more worker, and suddenly you're making 105 shoes, well, that worker's marginal product is 5 shoes. It's just the extra output from that one extra unit of input.
Now, there is a vital relationship between marginal product and average product, and I can almost guarantee this will be on your exam. Think of it exactly like your GPA in school. First, when the average product is rising, it's because the marginal product is greater than the average. That new worker is pulling the average up. Second, when the average product reaches its absolute maximum peak, it's because the marginal product is exactly equal to it. And third, when the average product starts falling, it's because the marginal product is lower than the average, dragging the whole team's score down. It's a very simple rule of 3 that dictates exactly how efficient your factory is at any given moment.
Which brings us to step 4, isoquants, mixing your inputs. This is where we start visualizing how managers mix and match inputs. An isoquant is simply a curve on a graph. Iso means equal, and quant means quantity, so it literally translates to equal quantity. Imagine a recipe where you need to bake exactly 100 cakes. An isoquant shows you that you don't just have one strict way to do it. You could use a ton of industrial ovens and just a few bakers. Or you could swap out some of those expensive machines for more workers doing things by hand and still bake the exact same 100 cakes. It basically represents all your different options for hitting your target.
Now, for your notes, here are the essential rules for how these curves behave. First, they're non-intercepting. They can never cross each other. Second, they're negatively sloped, meaning if you use less of one input, you absolutely have to use more of the other to keep output the same. Third, they're convex to the origin. That's a fancy way of saying there are limits to how easily you can swap humans and machines. This is called the diminishing marginal rate of substitution. And finally, a higher curve simply means a higher level of total output.
But what if you have a really unique production process? Well, linear isoquants represent perfect substitutes, meaning a machine can perfectly replace a human at a constant rate. Conversely, L-shaped isoquants mean your inputs are perfect complements. Basically, you strictly need exactly one worker per machine. Think about it. You absolutely can't substitute a second computer for the one person who actually needs to type on it. It just doesn't work.
And finally, step 5, the ultimate goal, profit.
All right, we've arrived at the final stage of our producer's journey. We've got our inputs, we understand our time frames, we know how to measure our workers, and we've mixed our recipes. Now it's time to win the game. Here is the formula that drives the entire business world. Economists love to use the Greek letter pi to represent profit, and the formula is super simple. Profit equals your total revenue minus your total cost. Let's break that down. Total revenue is just the price of your goods multiplied by the quantity you sold, so P times Q. Your total cost is the wage you pay your workers multiplied by the amount of labor, W times L, plus the rent you pay for your machines multiplied by your capital, R times K. Whatever is left over after you subtract your costs from your revenue, that is your profit. To achieve that maximum profit, academics love to talk about something called constrained optimization, or the dual problem of the firm. But as a business manager, you can just think of this as a simple two-step business strategy. Step 1, minimize your costs. You have to look at your isoquants and select the absolute cheapest combination of labor and capital for your target output. Basically, stop wasting money. Step 2, maximize your profit. Once you're producing efficiently, you choose the overall output level where the money coming in exceeds the money going out by the largest possible margin. So there you go. You have your producer's playbook. You know the theory inside and out. But I want to leave you with a provocative thought to chew on. We talked about how the long run allows you to change all of your inputs to optimize your factory. But if you have all that flexibility, what happens to your business and your profit when a massive technological advancement changes the game completely? The math might stay the exact same, but the real-world application is constantly evolving. Take these tools, apply them to the real world, and see what you can build. Thanks for joining me on this explainer, and keep questioning how the world works.